Hi everyone, welcome back to our channel. Today we are diving into another exciting project on physics informed neural networks, also known as PINs in short form. In this tutorial, we will be solving a system of ordinary differential equations, ODEs, using PINs. This video is designed to give you a complete understanding of both the theory behind PINs and the practical steps to implement them. I will guide you through every step of the process in detail. Though in this tutorial, we are currently focusing on this particular system of equations, the approach that we discuss in this tutorial is flexible and general, meaning you can apply this to a wide range of differential equation problems. Before we dive deep into today's tutorial, I have a small request. Behind every video, we do a lot of hard work to give you the best content. If you like our content, please consider subscribing to our channel. Your subscription means a lot to us and it really motivates us to keep pushing forward and create more useful tutorials like this. Let's dive into today's tutorial. First, let's start with a quick overview of pins. What are physics informed neural networks actually? Pins are special types of neural networks that incorporates the underlying physics of the system directly into the learning process. While traditional neural networks are trained purely on data, pins includes the residuals of the governing differential equations such as ODEs or PDEs directly into the loss function. These are the equations that we will be dealing in today's tutorial. These two differential equations combined with these initial conditions. So at t is equals to 0, we have x of 0 is equals to 1 and y of 0 is equals to 0. These equations describes how two variables x of t and y of t evolve over time with some interaction between them. Our goal is to approximate the solution using a neural network. I have taken this example from this reference. So here you see a lot of equations, but this equation is solved using the traditional analytical solving methods in this particular web page. So you can find the solution here, and the same example is solved using Laplace transform approach. So here this is the solution. So I used this solution as reference solution for verifying our neural network solution. Overall, the current time domain that I am considering in this tutorial is 0, 5. T starts at 0 and ends at 5. You can try out a different domain, so that's up to you. Before jumping onto the neural networks, so let's see how our analytical solution looks like. So as I said, these are the analytical solutions, so x of t and y of t. So here I have written a small program to visualize this solution. So our x of t looks like this and y of t looks like this. So we are going to use these solutions as reference solutions for verifying our neural network solution. So the basic idea of pins is very simple. What we will do is we will set up a neural network. A neural network consists of a particular input layer and some number of hidden layers and the output layer. In this particular example, the input layer consists of only one neuron, that is time, and here we define some number of hidden layers. You can define any number of hidden layers, so that's up to you. But one thing that we have to remember is as you increase the number of hidden layers and the number of neurons in each hidden layer, the overall learning process takes more time actually. So first start with some lowest number of hidden layers and some lowest number of neurons in each layer, and then over time, depending upon the accuracy requirements and depending upon the computational cost, we can optimize this number of hidden layers and neurons required in each layer. And in these hidden layers, you can use tanh or ReLU activation functions. And the output layer consists of two neurons, one specific to x of t and the other one specific to y of t. So overall, the network architecture is simple actually. So it takes time t and it outputs the values of x and y. This is the basic network architecture, and this network will learn to approximate the solutions x of t and y of t by minimizing a loss function, and this loss function is formulated using the residuals of ODEs and the initial conditions. By training the neural network, meaning by minimizing the combined loss, we ensure that the network learns a solution that satisfies both the governing differential equations and the initial conditions, meaning the neural network will give you a solution for x of t and y of t that satisfies these governing differential equations and these initial conditions. So here you can think of this neural network as a function, neural network function. In this entire architecture, as I said, to optimize the weights in the neural network, what we do is we minimize the loss function, and this loss function is very important. Formulating this loss function is very important. Let's see how we formulate this loss function. As I said, in this problem or any problem, we have a particular set of governing differential equations and some set of initial or boundary conditions. So we will formulate this total loss as a combination of residual loss, that is the loss that is obtained from the governing differential equations, and the loss that is obtained from the initial conditions. If we have additional boundary conditions, we will add that one also, boundary condition loss. So these are the two governing differential equations. So basically the idea is to, for example, if you have some functions x of t and y of t, and if you take the first derivative of it and apply these two summations, so you should get the final value as 0 at the specified time. And similarly, if you take the same y of t function, you should get this equation to 0. So what we do is we will consider this as a equation first actually. So first equation is this and second equation is this. So in the first equation, we just take the LHS term, that is dx by dt, 2x of t and y of t. What we will try to do is we will minimize this residual as much as possible and as close as possible to 0. That's how we formulate this residual of first ODE. And similarly, we will take the second equation and we take the LHS part and we are calling it as a residual of second ODE. As I said, the goal is to make this fx of t, fy of t to as close as 0. We are interested in directly making it to 0, but getting a 0 is computationally very expensive. So something near to 0 is sufficient for most of the practical purposes. And these two equations, this one and this one, fx of t and fy of t, are the residuals from ODEs. And when you look at the overall loss term, so what we are going to do is we are going to evaluate the residual at several points in the specified domain, and we will take mean squared error of each of the residual terms at these specified points. So putting this residual terms into this MSE, mean square error equation, so we get the loss from the first ODE and this is the loss from the second ODE. As I said, our objective is to get this close to 0. And the second loss that is coming from this initial condition loss. So we have two initial conditions, that is x of 0 is equals to 1 and y of 0 is equals to 0. So we are calling the first initial condition loss as ICX and the second initial condition loss as ICY. So basically what we do is we will just bring this one to left hand side and we will square on both sides, and that gives the first loss term. And similarly y of 0 minus 0, so basically y of 0 is equals to 0 actually. So we take a square here, that is equals to y of 0 square, and we expect this near to 0, and this gives our second initial condition loss. So what we will do is we will combine this and this into one equation. So here that gives our total loss. So overall our objective is to bring this total loss as small as possible. Here, as I said, we evaluate these residual losses at some specific points in this chosen time domain. So like Ti represent a specific point in the time domain. So we call these points as collocation points. So collocation points are specific locations within the domain where the differential equation and the boundary conditions are enforced. These points are similar to data points in a traditional machine learning context because we generate the data at these points. So how many number of points we have to choose and how many are sufficient? So basically there is no specific guidance on this. So you have to choose as maximum as you can, and choosing a less number of points will be difficult to solve this equation and get an accurate solution from the neural network. So we have to choose some sufficient number of points that we will get to know when we are working actually. First, we will do some iterations, like first we will choose some as I did here. So this T are the collocation points. So here first I tried with some 20 points, 30 points, 40 points and some more number of points actually. So overall I ended up using 100 points. So my point is like this 100 points are sufficient to get a decent accuracy in the solution. And also one point to highlight here is, so it's not just the number of collocation points that we choose defines the accuracy. There are many other parameters within the neural network like hyperparameters. So there are many other things that we have to take care to get the accurate solution. So this total number of collocation points are just one criteria. So first start with some low number and then slowly increase the number of points. And it is also worth mentioning at this stage about this universal approximation theorem. So this universal approximation theorem simply states that any neural network with sufficient number of neurons in the hidden layers and suitable activation functions can approximate any continuous function to a desired level of accuracy, meaning no matter what the function is, there exists a neural network that can get you very close to the correct output. This applies to any number of inputs and any number of outputs. So this is what universal approximation theorem is, and this is a very important theorem in physics informed neural networks. In fact, this is the theorem that gives power to the physics informed neural networks. So this is the overall work that we are doing in each epoch of the training. What we do is the neural network predicts the values of x of t and y of t at various points in time, and then we evaluate the derivatives of x of t and y of t with respect to time using a special concept called automatic differentiation. We get this automatic differentiation tools directly from the machine learning libraries like TensorFlow or PyTorch. So here in this tutorial we are using TensorFlow library. So these automatic differentiation tools are already available, so you can directly use them. And once we evaluate the derivatives, we have to compute the residuals, and then we evaluate the total loss function, and then we compute the gradients to update the weights of the network to minimize loss. And we repeat this process continuously until we get the total loss to a some lower number than the specified tolerance. So here we are using two special terms, like one is the epoch and the other one is updating the weights. So epochs are something like iterations actually. We repeat this process continuously. We repeat the process of optimization continuously. And in terms of optimizer, we can use any optimizer like Adam or lbfgs. This is the detailed walkthrough of pin algorithm. So as I said, these are our governing differential equations and initial conditions, and we initialize the neural network with a specific time t, and we expect the output to be x of t and y of t. Between these two, we have several hidden layers with nonlinear activation functions. And as I said, we use automatic differentiation to evaluate these derivatives. And after evaluating these derivatives, we compute the residuals such as fx of t and fy of t. After that, we evaluate the total residual loss and the initial condition loss. And then we evaluate the total loss. And once we have this total loss, we optimize the neural network using the Adam or lbfgs optimizer. And during this optimization process, we will update the weights of the neural network to minimize the total loss. And we repeat this process several times. And once we have sufficiently accurate neural network, and then we evaluate the x of t and y of t over a test domain using the train network, and we compare the results with the analytical solution if available. So finally we visualize the x of t and y of t curves. So here our main Python code starts. As I said, we use TensorFlow library. Here I define the basic neural network. So I'm calling it as pin, and this network consists of two hidden layers. So first hidden layer consists of 64 neurons, and the second consists of 64 neurons, and I'm using this tanh activation function at each neuron. And the last layer is the output layer that consists of two neurons, and each one corresponds to x of t and y of t, and this one returns the value of the network for a given t. So overall, this is our basic neural network actually. After that, here in this loss fn function, I'm evaluating the total loss obtained from the model at a given t. So what we are basically doing here is we are using this TensorFlow's gradient tape function to evaluate the derivatives dx by dt and dy by dt. After evaluating this two derivatives, we evaluate the residuals called resx and resy, and we evaluate the loss in the x function and loss in the y function at time t is equals to 0. So these are always same because initial conditions, right? They always exist at time t is equals to 0. Only the residuals from the ODEs change with respect to time. After that, I'm evaluating the mean square error here, and I'm taking up the total loss, meaning the summation of all these losses into this one term called loss. So I'm returning this loss from this total loss fn function. And next we create this train function. This train function takes four arguments. One is the model, time t, it's basically a vector, and epochs, and the optimizer. Here we do all these five processes. So in the first process, what we do is we will set up some number of epochs. So this all the remaining steps will repeat for this specified number of epochs, and in each epoch we evaluate the loss function and we evaluate the gradients from the loss function and we do the weight update, and then for every 500 epochs we will print the loss from the neural network. That's what we are basically doing in this train function. Here I am initializing this pin function into a variable called model, and after that here I am defining this optimizer. So in this tutorial we are using Adam optimizer, and a learning rate of 0.001 I am using here actually. So as I said before, we can choose any number of collocation points, but for now in this tutorial I have chosen 100 number of collocation points within the time domain 0 and 5. And here I am calling the train function with this four arguments, the model that I have initiated here, and the time t, the collocation point vector, and the total number of epochs of 4000 I am using here, followed by defining the optimizer. So optimizer, I have defined it here, it's a Adam optimizer. So overall at the end of 0th epoch, means first epoch, so we have a loss of 6.03, and after 500 epochs loss reduced to 0.0224, and at the end of 1000th epoch the loss further reduced to 0.0014, and at the end of 3500 epochs the loss is finally reduced to 10 to the power of minus 5. So any loss that is less than 10 to the power of minus 3 or 10 to the power of minus 4 is a decent expectation. We should always aim for such kind of values, and as you take more less values than 10 to the power of minus 3, like 10 to the power of minus 4 or 10 to the power of minus 5, our accuracy will increase, but that also requires more number of epochs to achieve that level of accuracy. I mean, for example, if you take 10 to the power of minus 7 as your target loss, so 4000 epochs are not sufficient. You may have to go for sometimes 7000 epochs or 8000 epochs, but when you increase the number of epochs here, the overall time taken for this training process will tremendously increase. So you have to choose your loss criteria to a reasonable limit. So after training here, we are creating this test entries. So here for testing I'm using the same t vector, so I just recreated it, but you can choose a different number of points here actually. Maybe you can choose 100 or 200 or 500, it doesn't matter. So as I said, you can choose any number of points here. So for example, here for training purpose I have chosen 100 points, and for testing purpose within the same time domain I have taken some 500 points. So I evaluated this true solutions from this equations for this entire test set, and then I'm plotting here actually. So this particular piece of code will give us this plot, and this particular piece of code gives us this plot. So what exactly are these plots? So this plot compares the analytical solution x of t with respect to the solution obtained from the neural network. So here I have chosen red color for analytical solution and blue color for pin solution. So if you look at here, so our solution is exactly matching with the pin solution. So overall, that's how we use physics informed neural networks to solve a system of ordinary differential equations. So in this tutorial, we have just scratched the surface here. There is a lot to learn in physics informed neural networks. Pins can be used to solve some highly complex advanced partial differential equations, inverse problems, and many more. We have planned a very detailed lineup of tutorials on pins, and we plan to cover topics like inverse problems, partial differential equation, and some methods like subdomain decomposition methods, and much more. But without your support, we cannot progress ahead. So if you found this tutorial useful, please give it a thumbs up. Let's aim for 500 likes on this video. And we know that at this stage, 500 likes for us is a very tough goal to reach. But we truly believe that with all your amazing support, we can absolutely make it happen. And if you have not subscribed yet, please consider subscribing to our channel so that you don't miss any of our upcoming content. We have a great lineup of tutorials coming up. Stay tuned. Thanks for watching. See you in the next tutorial. Happy learning.